is Evelyn Ramirez. I'm in Group 5 for the General Physics 1 lab, and my teammates are Angel Macario, Abigail Mosier, and Clarissa Ceros. So for the objective, in today's lab, we will be replicating prediction graph number 4 while analyzing the glider's movement on the air. The procedure was that we first began by balancing the track to avoid having peaks on our graph. As we balanced the track, we turned on the air compressor and made sure the sensor was connected in order to begin our graph replication. Each one of our team members got the chance to try to recreate the graph we chose to see who did it the best. Once we got the recording on capstone with our position versus time graph, we made an inference on how our velocity versus time graph would look like. We then compared our prediction of the velocity versus time graph to our actual position versus time graph that we made in capstone. So for the equations used, in order to predict what the velocity versus time graph would look like, we had to use the basic formula for velocity, which is velocity equals final position minus initial position divided by final time minus initial time.
Materials. For this lab, the equipment used was the Passport motion sensor, the 2-meter ruler, an air pump, a track, and a glider. Using the program Capstone, data was recorded using a position versus time graph and a velocity graph. The 2-meter ruler was to see the distance our glider was traveling, and the air pump was used to move the glider at a steady pace throughout the activity.
For the calibration process, we first need to establish a middle point on negative and positive values. To do this, we calibrated the floater at exactly 100 centimeters, as you will see in the next clip. The calibration process becomes clear. Another issue we addressed was the leveling of the track. By adjusting the structures at the bottom, we ensured the track was properly aligned. This step was especially important since any misalignment could affect the accuracy of our results.
That was good?
I think so.
These are our lab 2 results. This is a reference graph we got assigned, which is what we went off by, which was graph 1. And this is when we recreated the graph using the motion sensor. This is just an annotated version of this graph, which we have point 8 B and C annotated, which we will use for our tables. And we also have a little key just to know when we're going away and when we're going towards the center. With 1 is going towards the sensor, and then 2 is going away from the sensor. This is table 1, where we have our initial position, which is point A, change in direction, which is point B, and final position, which is point C, when we have here the time and the position in which they were. So for our initial position, which is point A, we were at 0 seconds and 0 meters. Our change in direction, which is point B, was at 4 seconds and -1 meters. And our final position, which is point C, was 12 seconds and 1 meter. This is table 2, which we found the change in position, the change in time, and the velocity. So from the line from point A to point B, we were at -1 meters in 4 seconds, which gave us 0.25 meters per second as a velocity. And the line from point B to point C was 2 meters in 8 seconds, and our velocity was 0.25 meters per second. And this is the little equation we use to find velocity. For table 3, we had to find the percent difference, and for that we needed the mean velocity values, which these we got off of the tool we use in order to graph our tables, and then this is what we computed by hand using the previous tables. So the line from point A to point B, we had calculated a negative 0.85 from when we created our graph, and from our hand calculator was 0.25, so that gave us a difference of 109%. And then the line from point B to point C was at 0.88, and the hand computed velocity was at 0.25 meters per second, which gave us an 111% difference. And this is how we found the percent difference. This is our prediction of velocity versus time graph, which here we have the positive 0.25, which is positive velocity, going positively with the origin, which is away from the sensor. And here we have negative 0.25, which is negative velocity, which is going towards the sensor, and is going the opposite direction of the origin. And this is a velocity versus time graph that we using it under the machine, And here we can see our mean values that we used in order to put them for our table. And here we can see like what our velocity time graph would be. So here you're seeing our position versus time graph, right below our velocity versus time graph. So for this, we can say that we weren't exactly correct on what our graph was, especially because we couldn't get the points exactly to what our reference graph was given, but we were pretty close to getting the nearest calculations.
One of the main challenges we faced was calibrating the machine to work correctly. The air blower's power affected the amount of friction the flag had on the track. This small detail was something we needed to carefully adjust. Another difficulty was figuring out how to push the flag at a constant speed. You're pitting a bird.
Are you set? Ready, set, go. That was too slow?
Damn. That's damn speed. The movement was very sensitive, and at first, we didn't know exactly how much force to apply. Finding that balance was essential to keep the results consistent.